Okay, folks, at the beginning of the last session, we talked about what happens when temperature increases. The molecules start moving faster, and something's got to give. Either the temperature or the pressure, or perhaps both, of the sample of gas must increase. Charles' law, we expressed the relationship between temperature and volume and said that as temperature goes up, volume also goes up as well. Now we're going to talk about the relationship between temperature and pressure. This is called Gay-Lussac's law, although it's not shown here. When volume is constant, the temperature and pressure and temperature, actually the absolute or Kelvin temperature, are directly proportional, which again means that as temperature goes up, pressure will also go up. This occurs in a rigid container, such as a spray paint can or shaving cream can. The volume cannot be easily changed. So if the temperature goes up, the pressure will go up. So as the temperature rises, because the volume cannot change, the pressure builds up. And if it builds up too much, then the can will explode. The graph and the equation for this relationship look very similar to the ones for Charles' law. As temperature goes up, pressure goes up. Temperature goes up, pressure goes up. And essentially it comes to a 0 point at absolute zero on the Kelvin scale, where there is no motion of particles. If there is no motion of particles, there is nothing to create pressure, so pressure is essentially 0. As with all equations in this chapter, our temperatures must be used in Kelvin. If I give you Celsius, add 273 and express it in Kelvin. This is a similar diagram to one that we saw for Charles' law, except with Charles' law, the piston was allowed to float and the atmospheric pressure was constant, so the volume could change. Well, now that piston is locked in place. The volume cannot change. So as we increase the temperature and the molecules start moving faster, since the volume can't increase, the pressure will increase. Here's kind of a real life example. A rigid sphere filled with gas and sealed off has been dipped and connected to a pressure gauge, has been dipped into an ice water solution at 0 Celsius, or more important, 273 Kelvin. And the pressure reads about 13 psi. So in here between 10 and 15, about 13 psi. That sphere is then moved to a beaker of boiling water, which is at 100 degrees C, or more importantly, 373 Kelvin. The pressure has now increased to about 17.2. It was about 13, now it's about 17.2. So based on the Kelvin scale, the temperature has increased about 30% or so. I'm sorry, the temperature in Kelvin has increased by about 30% or so. And the pressure has also increased by about 30% or so. So the pressure is directly proportional to the temperature in Kelvin. Here are some sample problems. Start off with a simple one. Gas has a pressure of this at that temperature. It is expressed in Kelvin. I change to a new Kelvin temperature. What will the new pressure be? Well, it's already in Kelvin, so I'm good to go. I simply plug it in. When you are submitting your homework, you cannot stop here. You must manipulate the equation and show me what P2 equals, what you are actually entering in your calculator. If you just give me this, it's coming back to redo. So please do it right the first time. All my numbers have 4 sig, so I express my answer to 4 sig. In this example, I have given you both temperatures in Celsius. You may be tempted to try to enter both temperatures in Celsius, but you cannot do this. It would, first of all, it would be incorrect. And second of all, you would have 1.25 over 0. How do you divide by 0 and get an answer? So anyway, you must change the temperatures to Kelvin. So I have now said that it's 1.25 at 273. I don't know at 423. Again, manipulate the equation. P2 equals 1.25 times 423 divided by 273. Put this in your calculator and make sure you do get the answer that's at the bottom of the page. I'd like to do one more example where we are solving for T2. I have an initial pressure and an initial temperature and an initial pressure. I have a new pressure. What is the new Celsius temperature? Again, you cannot plug Celsius into the equation. So I determine the original Kelvin temperature. Plug in my numbers, 1.65 atmospheres at 328 will equate to 3.65 atmospheres at T2. Again, you can't just give me this and copy the answer from the bottom of the page. Manipulate the equation. Cross multiply to get this equals that. And then you must show me what T2 equals, that this is what you're entering in your calculator. Remember that the answer you get will not be in Celsius. It will be in Kelvin. So the answer in Kelvin is 726. I must then convert that to Celsius by subtracting 273. So I hope you have paid attention on how to solve these problems, because your homework will be to solve problems regarding the relationship between temperature and pressure.